For centuries, mathematicians have been on this quest for a kind of holy grail, a simple, clean formula that could just spit out prime numbers whenever you wanted. It's a challenge that has felt, well, almost impossible, one of the biggest unsolved puzzles in the entire world of numbers. Today, we're going to look at a solution that is just shockingly elegant.
So, is there actually a formula for primes? Well, yeah, kinda, but most of them are just wildly impractical. They're basically just hiding a brute force search inside some super complex math. It's like building this enormous, slow-moving machine just to find a needle in a haystack. The real challenge, the real prize, is finding something that's simple and fast.
Okay, so let's get into this breakthrough. Back in 2008, a mathematician named Eric Rowland showed the world something truly remarkable. It wasn't some ridiculously complicated formula. Instead, it was a simple, beautiful little engine that, almost like magic, just starts churning out prime numbers from one incredibly basic rule. Now, what's really mind-blowing about this is just how simple the rule is. The next number in the line, r of n, is just the one before it plus the greatest common divisor, or GCD. And all that is the largest number that divides both our current step, n, and the previous number without leaving anything left over. We just kick the whole thing off with the number 7, and that's it. That's the entire machine. So let's actually watch this engine run. As you can see here, it all starts with 7. For the first few steps, if you look at that increment column, it's just adding 1. The engine's just ticking along, kind of idling. But then, at step 5, something amazing happens. The increment suddenly jumps to 5, a prime number. A step later, it jumps by 3, another prime. You see the pattern, right? The engine spends a lot of time doing nothing special, but when it makes a big jump, it's always a prime. And this, right here, is the core discovery. It's not the actual numbers in the sequence that matter, it's the jumps between them. Rowland proved that every single time the jump is bigger than 1, it is guaranteed to be a prime number. This little machine is a perfect prime sieve. But, there's always a catch, isn't there? The engine is beautiful, for sure, but it is incredibly inefficient. As we just saw, most of the time, it's just producing the number 1. It's like having to walk 1,000 miles just to find 3 little gold nuggets. So the big question is, can we upgrade this thing? Can we build a shortcut? This really shows you what we're talking about. On the left, you've got the basic engine just chugging along, one step at a time, wasting almost all of its energy. But on the right, that's the goal. A filtered search that can skip all the boring parts and jump right to the moments where a prime number is about to pop out. So, how do we build a shortcut like that? Well, this is where a really clever filtering technique comes in, called the Kitty system. Think of it like a special pair of glasses that helps us spot the most promising places to look. You see, almost all prime numbers, when you divide them by 12, leave a certain remainder. The Kitty system narrows its focus to just 2 of those, 1 and 5, because mathematically those are the richest, most promising spots to hunt for treasure. It's like going from searching a whole haystack to just a few handfuls of hay. Now here's where we fuse these two big ideas. We take the smarts of that KDI filter and we combine it with the logic of the Rowland engine. And what you get is a hybrid shortcut that lets you do something you could call algorithmic teleportation. We're not walking step by step anymore. We are literally jumping from one prime generating event to the next. So how does this teleportation actually work? Well, it's a surprisingly simple 3-step trick. First, the Kitty filter finds us a promising launch pad, a number n that has the right properties. Second, instead of running the sequence for who knows how many steps, we just do one quick calculation, 2 times n minus 1. And finally, step 3, we find the smallest prime factor of that result. And bam! That number is the very next prime the original slow engine would have taken forever to find. We just got there instantly. Now this is way more than just a cool mathematical party trick. This powerful new tool has a really high-stakes mission. We're now shifting gears into the world of modern cryptography, where finding very specific, very large prime numbers is actually a matter of global security. Let me introduce you to these Sophie Germain primes. A prime p gets this special title if 2 times p plus 1 is also a prime number. And these aren't just a curiosity, they're the absolute foundation for what we call safe primes, which are essential for the secure communication protocols that protect, all your online data. But here's the problem. Finding these pairs is incredibly hard.
I mean, just to give you a sense of the odds, this chart shows the probability from a real-world search project. The chance of a random guess being a hit is just 0.33%. You get an overwhelming number of misses for every single success.
And this is exactly where our shortcut becomes a complete game changer. By using the Kitty filter to focus only on the most promising candidates, we can essentially double our statistical odds of finding one of these pairs. We're making the hunt smarter, not just harder. To understand why this efficiency is so important, just look at this number, 10 to the power of 24. This is something called the mole rule. It's a rough estimate of the total number of logical operations performed by every computer in all of history, all put together. It represents a physical wall, a fundamental limit on what is even possible to compute. And this brings us to a really crucial point. For many of the biggest problems we face in math and computer science, these intelligent shortcuts, they aren't just a nice to have, they are an absolute necessity. Without them, some problems, like factoring gigantic numbers, would be physically impossible to solve, forever beyond our reach. All right, let's zoom out for a second. This elegant little algorithm does way more than just find prime numbers. It actually touches on some of the deepest ideas we have about complexity, about the universe, and about our own digital future. What we're seeing in the Roland sequence is a perfect mathematical example of a concept called emergence. You've got this dead simple local rule, just add the GCD, and from that tiny seed, this profound, complex, and totally non-random global pattern emerges, the prime numbers. It's the same exact principle that lets simple cells form a thinking brain, or simple ants build a complex colony. And that brings us to a critical, maybe even scary question for our modern world. The security of everything, our bank accounts, our communications, government secrets, it all relies on math problems that are just too hard for our current computers to solve. But what happens when a totally new kind of computer comes along that finds these problems trivial? Well, that's the threat of quantum computing. There's a powerful quantum program called Shor's algorithm that's specifically designed to crack the very math our security is built on, potentially making it all obsolete overnight. And this has started a frantic race to develop new quantum-proof security. And the core idea we've explored today, using smart filters to efficiently search for special numbers, is absolutely vital in building that next generation of digital defense. In the end, this whole exploration isn't just about one clever algorithm. As the source material puts it so beautifully, it's part of a journey of discovery into the digital DNA of our numerical universe. It's a reminder that hidden inside the simplest rules are patterns of staggering complexity, just waiting for us to find them. And that the search for primes is really a search to understand the fundamental code of reality itself.